In this lesson, we're going to learn how to balance equations. We're going to do a review from grade 10 balancing because balancing is going to be a very important skill going forward for chemical reactions in grade 11. So balancing was that idea that when you had a chemical equation, you had to have the same number of atoms on the left and right side. So you had to have the same number of carbons on the left side compared to the right side, same number of hydrogens, same number of oxygens, and then total would have to be the same as well. So let's just do a quick recap on how to count atoms within compounds and molecules. We actually did make a previous video to review that, so please go take a look at that if you need more information and more details on that. But a quick little practice here. So here we have zinc nitrate. How many total atoms are there? Well, there's one zinc. And then for nitrogen, don't forget subscript, multiply it by the subscript inside the bracket there. So 2 nitrogens, and then 2 times 3 here, 6 oxygens. So we have a total of 9 zincs, or 9 zinc nitrates. How many different atoms are in this compound? Well, there's a zinc, a nitrogen, and an oxygen. So there's 3 different atoms. How many zinc atoms? Well, we said 1. How many nitrates are there? How many NO3 units? This is NO3. You can see that there's 2 of them. There's 2 nitrates. Okay. If I had just written, let's say, Na, NO3, there's only 1 nitrate. So we can ask you that. We can ask you it in terms of individual atoms, but we could also ask you it in terms of the polyatomic ion, and that'll be important for balancing. How many nitrogens are there? So individually, there's 2 nitrogens. How many oxygens? Well, there's 6. And what's the name of this compound? I've said it several times. It's an ionic compound, so we name the metal first, then the polyatomic ion, nitrate. So let's go and take a look at this example here. Here we put a coefficient in the front, a big number in the front, right? Remember, subscripts are the small numbers, and then coefficients are the big numbers. And they basically tell you to multiply everything by 2. So here we have 2 units of zinc nitrate. If 1 unit, because this is 1 here, 1 unit had 9 atoms, then 2 would be 2 times 9, 18 atoms. Let's see if that actually works out. So for zinc, ignoring the 2, there's 1 zinc, but there's a 2 in front, so we have to multiply that by 2. So it's 2 zinc atoms. How many nitrates? Well, nitrates, there's 2, if you're ignoring the 2 in the front there. So there's 2, but then since there's a 2 in the front, you multiply that by 2, there's 4 nitrates. Because in reality, if you think about it, 2ZNO3 is just writing zinc nitrate out twice. So you have 2 here, that's 4. How many nitrogens are there? Well, if you were ignoring the 2 in the front, you'd have 2 times 1, 2 nitrogens, but you have to multiply it by 2 because there is a 2 in the front there, coefficient. So 4 nitrogens. And it makes sense. It's 2 times more than we had when there was 1. How many oxygens? Again, ignoring the 2 in the front, there'd be 6 oxygens, but there is a 2 in the front, so we have to multiply it by 2, and that's 12 oxygens. So our total number of atoms is 2 plus 4 plus 12. So that's 18. I didn't count the 4 here because that would just count the number of nitrates. I just counted the individual atoms to get 18, and that makes sense. And so this is zinc nitrate. That doesn't change the name. It's just we have 2 units of it. So putting a 2 in the front doesn't change the fact that it's zinc nitrate. Okay. The only thing that really changes the formula is if you change the subscript. If you change the small numbers, then you've changed the equation, you changed the formula, and therefore you've changed the identity of the substance. So you should be able to do a variety of practice problems with counting involved. I'm going to get you to pause the video and try these ones down here, just to see if you're on the right track. So I'll start with A. With A, there's 2 times 2, 4 hydrogens, and then 2 times 1, 2 oxygens for a total of 6 atoms. For B, well, there's 3 calciums. And then for nitrogen, there's 2 times 1 times 3, because it would have been 2 times, so 6 nitrogens. And then for oxygen, it's 2 times 3 is 6, times 3 again is 18. 18 oxygens for a total of 27. 27 total. So 3 calciums, 6 nitrogens, and 18 oxygens. Here we have a coefficient of 1, so we don't have to multiply there. We have 2 hydrogens, we have 1 sulfur, we have 4 oxygens for a total of 7 atoms. And lastly, aluminum carbonate. We have 3 times 2, 6 aluminums. For carbon, we have 3 times 1 and then times 3. So 9 carbons. And for oxygen, we have 3 times 3 and then times 3 again. So it's 27 oxygens for a total of 33 atoms, I believe. Nope, not 33, more than that. Let me go back and erase that. And so we have 27 plus 9, that's 36, plus 6, that's 42. So let me double check that. So if it was 1, it'd be 9 oxygens, 12 with the carbon in there, and then 14 with the aluminums, times 3 would have been 42. That's right. So why do we care about balancing? Remember, we just practiced some counting there because counting is an essential skill for balancing. Why do equations have to be balanced? Well, a chemical reaction follows something called the law of conservation of mass. It basically means that if you start off with a certain mass, you need to end up with the same mass. Stuff can't disappear. You can't destroy matter and you can't create matter. You can only kind of rearrange it in the different parts. So for example, let's say that my Lego piece here, this is 1 gram, 1 gram, and 1 gram. Altogether, there's 3 grams. When a reaction happens and they connect to make a new compound here, it's still 1 gram, 1 gram, 1 gram to get 3 grams. So a balanced equation follows the law of conservation of mass. If you look over here, we had 32 grams of sulfur and 56 grams of iron that we are putting together to react. And so the total mass here is 88 grams. So after the reaction has happened, we should have 88 grams of product made. Now, some of it might escape. It's important that if you really want to make sure that you have all that product made, you trap whatever's escaping. So, for example, if there was gas escaping, you would have to put a little cap on here, and you have to capture that gas in some way. But the point is that assuming nothing leaves, whatever you have before should be the same as what you have after. Okay, assuming nothing has left. And so here we have a skeleton equation. And we're going to do some quick counting just to see the problem with skeleton equations. I'm going to count atoms on both sides and compare. So on this side, I have 1. On the left side, I have 1 sodium. On the right side, I have 1 sodium. Great. So the sodiums are fine. I had 1 sodium, I ended up with 1 sodium. But here I have 2 chlorines. But on the right side over here, I have 1 chlorine. So we're somehow missing a chlorine. Skeleton equations aren't balanced. They don't follow the law of conservation of mass. So to make sure we're balancing it and the reactions happening in the right proportions, we need to follow the law of conservation of mass by balancing. And so balancing is a skill that involves you putting big numbers in the front to try to balance both sides, try to get the same number of atoms on both sides so nothing is missing. So let's take a look at what a balanced equation looks like. Here we have an example of a balanced equation, and we're going to count the number of reactants and products, the atoms on both sides. So for number of carbons in this reaction on the left side, we have 6 times 1, 6 carbons. On the right side, C6H12O6, this is 6 carbons. So same number of carbons, great. Oxygens, 6 times 2 is 12. 6 times 1 is 6. That's 18 total on the left side. On the right side, I have 6 oxygens here, and then 6 times 2 is 12. So 18. That's balanced. And then for hydrogens now, 6 times 2 is 12. 12 hydrogens. So 12 on the left side, the reactant side, in other words, and 12 on the product side. So my total number of atoms on both sides is the same, which means it's a balanced equation. 36 and 36. Nice and balanced, everything makes sense. So these are the general steps for balancing equations. You can read through these. We're going to do more practice problems together. Some general tips that I give is try balancing the atoms that occur in the largest number on either side first, and leave things like hydrogen, oxygen, and other elements till later. If you have polyatomic ions that appear on both sides, try to balance them as a group. Try to balance them without having to count them individually. It makes things a lot easier. And then if you have any oxygen afterwards or hydrogen afterwards, then go ahead and try to balance those. So you can follow these general tips here. One of the biggest tips I can say is always verify at the end that things are actually balanced. So just do one final count before moving on to make sure everything is nice and balanced. And make sure your work is organized. Use a pencil, erase things if you need to, be nice and clear. So let's go ahead and try a simple balancing first. You can use a table like this. For me personally, I like to just count the number of atoms on the bottom um, while I'm doing this work. So for example, I'll do, okay, one sodium, two chlorines, one chlorine, sorry. So let me see already, there's a mistake there. So I'm just gonna erase it neatly. One chlorine here. So my sodiums look fine, but my chlorine is off. You cannot modify the equation by changing a subscript. You can't put a 2 by the chlorine there at the bottom here. You can't do that. You can only change coefficients. So I need 2 chlorines on my right side. Right now there's only 1. A coefficient is going to multiply everything in the equation. So sometimes it's a bit of trial and error, but if you're good at math, you'll right away picture that if I have 1, I need to multiply it by 2. So I'm going to multiply this whole thing by 2 here. And I'm going to change my numbers here. So now I have 2 times 1, 2 sodiums, 2 times 1, 2 chlorines. My chlorines are good now. I have 2 chlorines on this side and 2 chlorines on the left side. But you'll notice my sodiums are off now. I need 2 sodiums on the left side. So I can put a coefficient of 2 here, and that's going to be 2 times 1, 2. So now my sodiums are balanced. This 2 will not affect that chlorine there because they're separated by a plus. The coefficient will only affect both substances if they're not separated by a plus, if they're in the same compound. So this is balanced now. Just to double check, I have 4 atoms on this side and 4 atoms on this side. You could keep track of them in a table as well. That can work. So you might say, for example, initially I had 1 and 2. On the product side, I had 1 and 1. After putting the coefficient of 2 on the product side, I now have 2 and 2. Now my sodiums are off, so I have put a 2 on the Na on the reactant side, and I have 2 and 2 again. And then everything is finally balanced. So you could keep track of it in a table. Again, I prefer to just keep track of it and just cross things out as I modify in that form there. Generally, one more thing to mention is if you didn't have to put a number in front of it, so let's say I put all these lines here for you to write an answer, I would just put a 1 anyways, just to let me know that you knew that I didn't have to change it. I could just leave it as 1. Let's do a couple more examples. So here we have zinc and silver nitrate reacting to make zinc nitrate and silver. Let's start off by counting first. But before we do that, actually, I want to mention something. You'll notice that we have nitrates appear on both sides. So you could balance by tracking each individual atom, like how many nitrogens are there, how many oxygens. You could do that. But because nitrates appear on both sides, you can treat this as units of nitrate. So for example, here I have 1 nitrate. Here I have, well, 2 nitrates. Let's look at my zinc. Zinc I have 1. Zinc I have 1. Silver I have 1. Silver I have 1. So zincs match. Silvers match, but nitrates don't. I need 2 nitrates here. I need 2 nitrates over here. I somehow need 2. So this is where there's a problem. So what I can do is simply put a 2 in the front. And so when I do that, now I have 2 silvers and 2 nitrates. So my zincs are still good. My nitrates are now great. So zinc is good. Nitrate's good. But now my silver's off. I have 2 silvers on the reactant side and 1 on the product side. So I need 2 on the product side, so I can multiply this by 2. And now that silver's balanced. So my zincs are balanced. My silver, I have 2 on this side, 2 on this side, balanced. My nitrates, 2 times this group here. 2 nitrates, good. And then 2 nitrates here. Where I didn't have to put a coefficient, because I put a line there, I'm just going to put a 1. Because I didn't have to modify that in any way. And you could go and count the individual atoms and make sure your number of atoms make sense and add up. So for example, 1 zinc and 2 silvers. And then nitrates I have, within the nitrate, I would have 2 nitrogens and 6 oxygens. So 2 plus 6 is 8, plus 2 silvers, that's 10, plus 1 zinc, that's 11 atoms on this side total. Over here I have so 2 silvers, I have plus 6 oxygens, that's 8, plus 2 nitrogens, that's 10, plus 1 zinc, that's also 11. So my atoms also, total number of atoms, add up correctly as well. So you could have done this individually, but that's a nice easy trick to remember. If the polyatomic ion, the exact same one, appears on the other side, treat it as an individual unit to save you the trouble of having to go and do that individually. So let's try this one out here. Let's start off by counting first. I always count. Sometimes I might give you a reaction and it's already balanced. So if you start balancing from the get-go, you're just doing more work than you need to do. So here I have 1. Here I have, on the other side, I have 1 as well. My fluorine is 2. And my fluorine on the other side, on the product side, is 3. So my aluminums are okay, but my fluorines are off. So I need to find some number, some multiple with 2 and 3. And the easiest way to do that is just to do 2 times 3. Right? 2 times 3 is 6. That's the way I can connect the 2 and the 3. So, for example, if I put a 2 over here, now I have 2 aluminums and 6 sulfurs, because 2 times 3, 2 times 1. Okay, well, I can make a sulfur. I can make 6 sulfurs on the left side. I can simply do, I have 2 already. If I put a 3 here, that's now 6. So my, I think I'm saying sulfur. I don't know if I said sulfur or fluorine. F is fluorine. So over here we have 6 fluorines on both sides. That's balanced. Our aluminum is no longer balanced because I have 2 aluminums on the product side right now. So I need 2 aluminums on the reactant side. So I can put a 2 here, and that gives me 2. So this is 2 and 2, 6 and 6. We are not balanced. We have 8 atoms here and 8 atoms here. So sometimes you might have to find a common factor between the 2 and the 3, or between a number, and the best way is simply to multiply them together to do that. One thing I want to mention is that some students in the past have done this. They said, well, this is balanced as well. Right? You have 4 aluminums, 4 aluminums. You have 12 fluorines, 12 fluorines. Yeah, it's balanced, true. This would have worked as well. Just make sure when you're balancing, you get the most reduced form possible. So you'll notice you can divide everything here by 2, by 2, by 2, and that will give you back your 2Al plus 3F2 produces 2AlF3. So you can do that. It has to be the most reduced form possible, kind of like with ionic compounds. Let's try this one out over here. So again, you can try this yourself. You can pause the video and try it out yourself. I'm going to start off with counting. So calcium, 1 and 3, they're not balanced. Chlorines, 2 and 1, they're not balanced. Sodiums, 3 and 1, they're not balanced. Phosphates appear on both sides, 1 and 2, they're not balanced. So there's a couple ways you can approach this, and you have a lot of choice, and different ways will lead to the same result. I'm going to try to balance my my phosphates first. My polyatomic ion, I have 1 here, and I have 2 here. So I'm going to put a 2 in the front over here, and so that's going to lead me to 6 sodiums and 2 phosphates. So my phosphates look okay. My sodiums are off now, though. So I'm going to jump immediately to go try to balance the sodiums. It's like I'm going back and forth like ping pong here. So 6 sodiums. I'll get 6 sodiums on this side by doing times 6 here. And so that'll give me 6 sodiums. That's balanced. But now I have 6 chlorines. So I'm going to jump to the other side to balance my 6 chlorines. So let me put a 3 there, because now I get 6 chlorines because everything multiplies by 3, right? So that becomes 3 calciums and 6 chlorines. So my chlorines are now balanced. And if you look, it worked out. My calciums are also balanced. That means I don't really have to do anything else to this, so I'll just put a 1 over here because I don't have to modify it in any way. The thing about balancing is that it's like a puzzle. You'll find the answer as long as you're following the strategies. And if you make a mistake, you just erase and retry. So some of you may have tried to balance the sodiums first. You would have put a 3 in the front of NaCl, and then you would have said, okay, well, now I have to balance my Cl somehow. And you would have had to go back and try to figure out how to balance your Cl. You would have said, well, there's no way to get 3 Cls here, so maybe I need to retry that. Maybe I need to find, if I have 3 Cls here and 2 there, I need 6 Cls total. So then you would have to erase your 3 over here and then come up with a 6 instead. So basically, there's many ways you can approach it. You don't want to put any decimal values, but there are cases where you can put a decimal value as a trick to help you balance the equation, and I'll show you that shortly. So let's try this one out here, so you can pause the video and try it yourself. So once again, we can count 1 aluminum, 1 aluminum. That's balanced. Nitrates, we have 3 nitrates, 1 nitrate, not balanced. Ammoniums, we have 3 ammonium here, 1 ammonium here, not balanced. 1 phosphate, 1 phosphate. Phosphates are balanced, and so are aluminums right now. I'm going to try to balance my nitrates, or sorry, my ammoniums. I need 3 ammoniums, so I'm going to put a 3 over here. And so now I get 3 ammoniums and 3 nitrates. And so now, let's go to the other side here. You'll notice that my ammoniums are balanced. And if you look at it carefully, my nitrate is also balanced. And it looks like everything else is nice and balanced. My phosphate is balanced. My aluminum is balanced. So there's nothing else I need to do. So I'm just going to put 1, 1, 1 here. So now everything is nice and balanced. Aluminums are balanced, nitrates are balanced, ammoniums are balanced, and phosphates are balanced. So sometimes just that practice and having enough experience lets you select the move that'll lead you to the answer quicker than other moves. Now, this one here is a bit tricky. These ones are probably the most difficult ones to balance because you have O's split up in different areas here. It's tough overall. So I'm going to show you a trick when you have something like this. You might get it with trial and error, but it'll take you a long time unless you use this trick here. So this is typically when you have these combustion style reactions where the oxygens are split like this. What I'm going to do first is I'm going to balance everything but the oxygens right now. So I'm going to put a 4 here. And I'm going to put a, let's balance the hydrogens next. I'm going to put a 4 over here. So my carbons and hydrogens are balanced. But now for oxygens, let's just count how many I have on the reactant side. I have 4 times 2, 8, 4 times 1, 4. I have 12 oxygens here, okay? And on this side, I have 1 and 2, I have 3. Now, I don't want to change anything here because I have my carbons and hydrogens balanced, so I don't want to modify this. But I want to work on somehow getting the right number of oxygens with this one here. I want to get 12 oxygens total. Now, you can't put 6, because if you put 6, that's 12 plus 1, that's 13, you're off. So basically, you want the one that's over here to add up to 12. You want to somehow get 11 here. Okay, you want to get 11. So I want to somehow put a number in the front that when you multiply it by 2 will give you 11. And if you think about it, that's going to be, there's 2 ways you can write this. You can put 5.5 or 11 over 2, right? Because when you multiply 11 over 2 times 2, that crosses out here, you get 11. Okay. So right now, this is balanced. So you have 12 oxygens and everything else is balanced. But the problem is you can't leave this with that decimal value there, with that fraction coefficient. So how do we get rid of it? We multiply everything by 2. So if you now multiply this entire equation by 2, you have 2C4H8O plus 5.5 times 2 is 11 O2s, 8CO2 plus 8H2O. So I've multiplied the entire equation, all the coefficients, not the subscripts, the coefficients. When you multiply an equation, you're multiplying the coefficients only, not the subscripts. And you can go and count to make sure everything makes sense. So here I have 8 carbons, balanced. 16 hydrogens, 8 times 2, 16 hydrogens, balanced. Okay, for oxygens, I have 2 over here, because 2 times 1 is 2, and 22 over here. It's 24, because 11 times 2 is 22. Add these two together, 24. Here I have 8 times 2, that's 16 oxygens, and 8 times 1, that's 8 oxygens. That's 24. 24 O's. Nice and balanced. So that's a trick you can use if you run into an equation that's a bit tough to balance, especially these like here. These ones like here, if you see a fraction will work, do it and then multiply the entire equation by that first number. That'll get rid of that fraction and make sure it's the most reduced as possible. And then you have a bunch of practice problems that you can do here. So these practice problems, I recommend you pause the video, try it yourself, and then take a look to see if I'm on the right track, if you're on the right track with what I did. So this is essentially just writing a word equation, then converting it into balanced. So hydrogen gas reacts explosively with chlorine gas to give hydrogen chloride gas. So my word equation is going to be hydrogen plus chlorine. Remember, we don't put the states when you're writing word equations. Produces hydrogen chloride. So I'm going to write my balanced equation. Before I balance it all out, I'm just going to write like a skeleton version of it first. So H2 gas plus Cl2 gas, because there's a Hofbrinkel. And then hydrogen chloride, HCl gas. And then I'll go about balancing it. So I have 2, 2, 1, 1. Put a 2 in the front and you'll notice that solves your whole problem. So there we have a balanced reaction. Let's try B. Potassium chlorate breaks down to form potassium chloride and oxygen gas when heated. So potassium chlorate, that's our reactant, is heated. Oftentimes we can put the word heat on top or a triangle to indicate heat. That means like a change in temperature or heat. And that'll give you potassium chloride plus oxygen. And states are given, so we'll put that in our balanced equation. Balanced equation do take states, just like skeleton equations, but the difference is we balanced it. So potassium chlorate, if you do your crisscross, you get KClO3. That's solid. You decompose it. Let's put heat there. You could have put plus heat as well, but don't let that confuse you. You're not going to balance the heat. Crisscross, you get KCl, and it's solid form, plus oxygen O2 gas. And so you can balance this. This looks a bit tricky at first. Our Ks and our Cls are balanced, so it looks good, but our oxygens aren't. So between 3 and 2, 3 times 2 is 6. So let's aim to get 6 oxygens. So I'll put a 3 here. That'll give me 6. I'll put a 3 here. That'll give me, a 2 here. 2. That'll give me 6, 2, and 2. So my Ks and my Cls aren't balanced, but if I put a 2 here, that fixes everything. And there's a balanced reaction. Let's do this example here. Ammonia gas can be made by combining hydrogen gas and nitrogen gas. So be careful here. We wrote the product first, but the way this is worded, this is the product, right? We're making ammonia from hydrogen and nitrogen. So hydrogen plus nitrogen can be combined to produce ammonia. And so now we can write down our skeleton equation first, H2 gas, because it's diatomic, N2 gas, and then NH3 gas. Let's see if it's balanced. It doesn't look balanced. I'm going to try balancing the... Doesn't really matter which way I go. I could start with the H's. I could start with the nitrogens. So if I start with the nitrogens here, I have 2. I need 2 here, so I'll put a 2 there, and I'll get 2 and 6. So the nitrogens are balanced, but my hydrogens aren't, so I'll put a 3 over here, and now that's 6. And so now the nitrogens are balanced as well, or the hydrogens and nitrogens are balanced. And so now let's finish off with this example here. We have aluminum metal reacts with oxygen in the air to form a hard coating of aluminum oxide. So our word equation is aluminum with oxygen, and it's going to produce aluminum oxide. So I'm going to write my skeleton equation first. Aluminum, metal is not the state, it's just a class. But if you go in your periodic table, you'll see it's in black font. So typically at room temperature or at most temperatures we're dealing with, aluminum will be solid. So it's a safe assumption to do that. Oxygen is a diatomic molecule in the air, it's gas. Aluminum oxide, 3 plus, 2 minus, crisscross it, and you get Al2O3, and it's a hard coating, so solid. And we need to balance this. So I'm going to start with my oxygens first, actually, because I can see oxygen, when I try to balance, it's going to affect my aluminum. So I'm going to deal with oxygen first, so that way I can affect aluminum after. If I had balanced my aluminums first, I would have to go back and modify aluminum in the compound, and that would change my oxygen, and I have to erase a whole bunch of stuff. So let's start with oxygen first. We have 2 and 3. A good thing to do is 2 times 3 is 6. So if I put 2 here, that's 6 oxygens. 3 here, that's 6 oxygens. Nice and balanced. Aluminums, I now have 4, because 2 times 2 is 4. So now I can go here and put a 4, and that's 4. So that's balanced as well. And so those are just some more examples of writing word equations, skeleton equations, and balance equations with proper states and proper coefficients when doing that. And just to show anywhere I didn't balance, I'm just going to put a 1 just to show that I'm done balancing. That's what I like to do because I make a lot of mistakes sometimes when I do my work. And so if I just finalize by putting 1s in places, even though I don't really need them, I know that I'm done my balancing. I didn't skip it and had to come back to it.